All right, we'll go ahead and get started. This is our another presentation from one of our platinum sponsors, SIGOPT. We have Meghana Ravikumar. She is an ML engineer with SIGOPT, and she will be talking about efficient BRT today. So without further ado, Meghana, the floor is yours.
Okay, great. Hi, everyone. Thanks for tuning in. I know it's been a long week, so we'll just get right into it. Today, we're going to be talking efficient BERT, finding your optimal model with multimetric Bayesian optimization. Again, I'm Meghana. I'm a machine learning engineer at SIGOPT, and these are my handles if you want to chat. So during this talk, we'll explore how to reduce the size of BERT while retaining its capacity in the context of question answering tasks. So we'll be pairing multimetric Bayesian optimization with distillation and show that by concurrently tuning competing metrics like accuracy and model size, we are able to distill BERT and assess the trade-offs between model size and performance in a granular fashion. So before we jump into the use case, I'm just going to quickly go over what we do at SIGOPT and the product features we'll use for this use case. At SIGOPT, our mission is to amplify and accelerate your model development and to help you gain insights throughout your experimentation process. So we understand that modeling is messy and difficult to standardize, that training can be a crapshoot and difficult to debug, and that tuning is expensive and difficult to scale. And we've built solutions to help with these problems, including intelligent experiment management to organize and collaborate with your team throughout your modeling process, providing insights into your training runs, and efficient, intelligent, and scalable hyperparameter optimization. And we know that you're iterating on tooling along with iterating on your model development, and we've made sure that we're easy to use and stack agnostic. For this talk, we'll focus on hyperparameter optimization at scale. So here's how our general optimization loop works. We set up our parameter space. SIGOPT samples this space and provides parameter values. We run our model training with these suggestions and return the model's performance or other metric back to SIGOPT. The optimization proceeds in this loop-like fashion where over time, we should see our model performing better and better. Great, now that's done, and we're more familiar with the tools we'll be using. Let's talk about distilling BERT. So BERT is great and is a very pivotal architecture. It is generalizable and transferable, which means that the model performs strongly across a variety of NLP tasks with very minimal changes required in its architecture. So this really enables us to use techniques like transfer learning and leverage large pre-trained models to solve specific and niche problems, which is really convenient. But on the other hand, it is very large and difficult to put into production systems and other memory-constrained applications. So many teams are trying to solve this problem by compressing or distilling BERT, including Hugging Face, Raza, and Utterworks, to list a few. And we'll be focused on expanding Hugging Face's work on distilling BERT and specifically ask two main questions. One, can we understand the trade-offs between model size and performance when distilling BERT? And two, given these trade-offs, can we make informed decisions on a model architecture that best works for our needs? So to answer these questions, let's focus on our use case, distilling BERT for question answering. So the data set we'll be using is Squad 2. It is comprised of 35 topics ranging from the chemical properties of oxygen to the history of the Yuan dynasty. So each topic has a set of questions the model needs to understand and answer. You can think of this as your standardized reading comprehension test, where you're given a paragraph and a set of questions, and you need to find the answers to these questions within the paragraph. Unlike Squad 1, Squad 2 introduces the concept of unanswerable questions, making it more challenging for models. The data set is split between 50-50 between answerable and unanswerable questions. For answerable questions to be marked as correct, the model has to find the exact string match within the passage. But for unanswerable questions, the model really has to only classify that data point as unanswerable. This is not great, as the model can randomly guess that all answers are unanswerable and get a 50% accuracy. So we'll deal with this property of the data further down the line. For now, let's take a look at how distillation works. So distillation is a technique that's used to reduce the size of models, where a large, cumbersome model, the teacher model, is distilled into a smaller model, the student model. So during distillation, the teacher model is typically already trained on the data set, and the student model is being trained through the distillation process. Unlike most model training processes, the student model's loss function is a weighted loss over hard and soft target losses, where the hard target loss is just your classic loss function where the model is trained on the data set. And the soft target loss is this added component that allows the student to learn properties that the teacher model has already learned. So by combining both types of loss functions, the student uses this information to generalize the same way as the teacher model and reach higher model performance than if it were to just be trained from scratch. So the overall goal of distillation is to get a trained student model that is smaller than the teacher model and performs strongly on the given data set. So we'll be using distillation as our technique to reduce the size of BERT, and we'll be running it multiple times with different student model architectures to really understand which model architecture works best. So our teacher model is BERT, pre-trained and fine-tuned on Squad 2, and we perform an architecture search during our optimization process to define the student model for each distillation cycle. So due to how distillation works, we also expect the student model to have learned properties from the teacher model that it would not have been able to learn on its own. And a quick shout out to Hugging Face. Without their Transformers package or their prior research, this project would not have been possible. So I highly recommend checking them out. So now that we have defined our distillation process at a high level, let's look at how we're going to define the student model. We define the student model's architecture through suggestions from SIGOPT, where SIGOPT provides suggestions for the student model architecture as well as the hyperparameters. So it'll tell us basically like how many layers should we use for this training cycle, as well as like what are the SGD parameters, for example. And as much as we can, we seed the model with pre-trained weights from Distill BERT, trained on the Toronto book corpus and English Wikipedia. So now that we've designed our distillation process, let's look at what our baseline is. For the baseline, we use the student model architecture from the Distill BERT paper. The distillation process itself uses a low temperature and an equally weighted loss function across the hard and soft target losses. And the SGD parameters used are also the defaults from the Distill BERT paper. So we're really just trying to keep everything as constant as possible. As a result, our baseline has around 66 million trainable model parameters and reaches a 67% accuracy on Squad 2. And by optimizing this distillation process, we're going to see if we can beat the baseline's accuracy and come up with a student architecture that's smaller than 66 million parameters. So let's take a look at our optimization cycle. As I said earlier, we're going to use SIGOP's HPO solution, and specifically multimetric Bayesian optimization. So to optimize the distillation process and perform our architecture search simultaneously. With this hyperparameter optimization technique, we're able to optimize for two competing metrics at the same time. And at the end of the optimization process, it'll populate a Pareto frontier, where each point on the Pareto frontier is an optimal trade-off point where you cannot improve in one competing metric without sacrificing the other. More concretely, what that means for us is that we'll be concurrently optimizing for model performance versus model size, where we want to increase model performance and decrease model size of the student model. On the graph, we see again the baseline values for each metric that we are trying to beat. As we already know, the Squad 2 dataset is split across answerable and unanswerable questions. This just means that if the model is trained poorly, it's really easy for it to fall into this hole of classifying everything as unanswerable and randomly be correct 50% of the time. So there are a couple ways to deal with this. We could create a better composite metric that measures model performance across the two categories more accurately, or we could just use SIGOP's optimization feature called metric thresholds. And because composite metrics are difficult to create, we chose to set a metric threshold at our 50% accuracy point. So what this does is it really informs the optimizer to focus its efforts on parameter space values that result in a model accuracy over 50%. And that means we can successfully avoid configurations where the model is randomly guessing. So what are we tuning? So we'll be tuning training parameters, including parameters for SGD, batch size, and weight initialization. We'll be tuning architecture parameters that include the number of transformer blocks, the number of attention heads within each block, attention head pruning, and dropouts for the network. And we'll be tuning the distillation parameters for temperature and the weights for the soft and hard target loss components. So at the end of this optimization experiment, our Pareto frontier will be optimal sets of model architecture and hyperparameter configurations, where we cannot improve in size without sacrificing performance, and vice versa. So this is just an overview of our optimization cycle. SIGOPT provides distillation, architecture, and other hyperparameter suggestions. We create the student model and run the distillation process given these parameters. The resulting trained model reports back its validation performance and size. SIGOPT then takes these performance metrics and suggests the next set of parameters, which include, again, distillation, architecture, and other hyperparameter suggestions. And we continue in this loop-like fashion until the end of the experiment. So in order to conduct this experiment, we use Ray to orchestrate our EC2 cluster. So Ray manages the cluster orchestration and uses SIGOPT for the parallelized Bayesian optimization algorithm. And we run our tuning process in parallel across 20 EC2 instances. So what were our results? So this is our resulting Pareto frontier. The yellow dots are the optimal points, and the pink dot is our baseline that we had previously established. By using this frontier, we're able to understand the trade-offs between model performance and size during distillation. We're also able to identify architecture configurations for the student model that result in these trade-offs. Essentially, instead of relying on a single architecture performing well for question answering, we're able to leverage these trade-offs and choose from a set of architectures. So these are just a few optimal points I wanted to highlight. On the far left, we have our smallest student model architecture that performs as well as the baseline. And on the far right, we have our best performing model that is slightly larger than the baseline. So here are the respective architectures for those optimal points. Some common features found between the optimal configurations include the student model preferring no dropout and an emphasis on soft target loss. So it's weighting learning from the teacher model more so than the data set. And we see that the architecture is compressed more often by reducing the number of layers and more so than pruning the number of attention heads. This one's more intuitive because we're trying to reduce the size of the model and layers are larger than the attention heads. So what we see here is that by leveraging multimetric Bayesian optimization to conduct an architecture and hyperparameter search during a compression or distillation process, we're able to identify sets of viable models for our specific problem. And we're able to choose the model architecture that best suits our needs. So we're going to take a quick look at our dashboard. So here we're able to, if it loads, able to see our Pareto frontier. We're able to analyze patterns between specific parameters and the metrics that we choose. And I think a more important part is this parameter importance that kind of tells us which parameters more likely and have higher influence on each of the metrics that we care about. So here we see the number of layers being the parameter that kind of differentiates what are we getting as an accuracy as well as what is the model size, which makes sense. And down here, we can really use our parallel coordinates chart to really identify sweet spots for parameter values that we can leverage for either this experiment or experiments in the future that might have similar parameter spaces. So this is all great, but we really want to know, was the model able to answer questions? So let's take a look at our best performing model. So our best performing model hits at 70% accuracy. As we see in the graph, depending on the category, the model performs better or worse, with topics such as the Yuan Dynasty, Warsaw, and steam engine being more challenging than others. To understand what's really going on, we're going to categorize misclassifications into 4 categories. Mostly right, the model is off by either including more context words or things like punctuation in its exact match, identification of the answer. Mostly wrong, the model has gotten the answer completely wrong. Label no answer, the model predicts an answer despite it being unanswerable. And label has answer, the model predicts no answer when the question is answerable. So although some categories have different majority misclassifications across the categories, most of the errors we saw are label no answer, which means that the model was answering questions that in fact are unanswerable. So this is interesting because going back to why we set the metric thresholds, we were really worried about the model randomly predicting that everything is unanswerable. So it seems to have taken care of that problem, but is now running into this new one. So let's take a closer look at why the model tries to answer questions that are in fact unanswerable. So this passage on Warsaw is a pretty good example of the patterns that I saw. So the section spans a long period of time with complicated and convoluted historical events. We see very similar nouns in each section take on a different role. So the main entity, the city of Warsaw goes through many transitions and many different terms are used to describe the same place. And in addition to that, the questions are tricky and do ask about relationships between these overloaded terms. So for example, in the passage above, one answerable question is whose army liberated Warsaw versus one unanswerable question is whose army liberated Duchy, where the text says Duchy of Warsaw and the model guesses Napoleon for both. So these entities are related, but have nuances between them that the model isn't able to pick up. It's not able to differentiate between Warsaw and the Duchy of Warsaw, or really understand that these differences are due to a temporal transition that is described in the passage. And many missed questions similarly follow this pattern, and it's definitely something to look into for future work. So why does this matter? By using scalable and intelligent hyperparameter optimization, we're able to easily understand trade-offs made during a compression process or distillation process. And by understanding these trade-offs, we're able to choose a model architecture that best suits our needs. For more on this project, please go to our blog. There's like the full analysis on it. And there's also a GitHub repo and published PyTorch model checkpoints that you can use for your own projects. And you can explore the experiment dashboard as well. This link is public, and please feel free to play around with that. And for a limited time, you can sign up to use SIGOPT for free. So if you're interested, please join our free beta. And thank you. And now I'm going to open it up for any questions. Although I don't know how to.
Thank you, Meghana. I'm looking here in the chat and see if any questions pop up for you that we can handle. Alternatively, if questions do show up in the chat room, I would encourage you to answer them one-on-one via the chat feature.
Cool.
So I want to thank you very much for the informative presentation. We appreciate the support with your sponsorship as well. This actually concludes our ML and business track or sessions for the day. However, we have another presentation on the main stage starting at 3:45, and we also have one more session in the ML Sciences track as well that starts at that 3:45 time frame. And we will have a startup showcase at 4:15 at the conclusion of those other two presentations. So I hope that you guys stick around for that, and I believe we're going to have some giveaways during that time frame as well. So Meghana, thank you once again. We appreciate it. I hope you guys enjoy the rest of the conference.